Record. Okay. Okay. Find the flux through a closed surface. So first, let's take a quick look at this question. So which closed surface or surfaces have zero electric flux? So that is relatively easy question. Which one do you think is zero? Zero flux? Okay, let's see. So who selects option A? Or B? Or C? Or D? Okay. First, let's see the answer. The answer is A. Let's see. So first of all, what's the direction of this surface? The direction of the surface vector is in this direction. So what's the theta between E and dA? This is direction of E. So that's theta. It's greater than 90 degrees. So cosine theta is positive or negative? It's a negative. When theta is between 90 and 180 degrees, cosine theta becomes negative. And in another case here, dA goes in that direction, and the angle between dA and your E is less than 90 degrees, and cosine theta is positive. So on the left surface, you get negative values of the flux. On the right, you get positive. So finally, in this case, get let's take a look at B, option B. It's perpendicular to the surface. So is it positive or negative flux on the right side of the surface? Positive, because E and dA, they have the same direction. Then you get positive flux. So the same thing for left side and the lower side. So you always get positive values. So for option B, you get positive net flux. And for C, you get negative net flux, net electric flux. Now let's do a calculation together. The flux integral through a spherical Gaussian surface, which is shown here, centered on single point is E dot dA, and then surface integral. As we discussed in previous slides, if the E is always perpendicular to a surface, and the magnitude of E is constant, then your integral could be written as EA. Because E is constant, you can take it out, and E and A, they have the same direction. So cosine theta is always a 1. The same thing here. E at the surface is always, let's say, a constant in magnitude. And the direction is always perpendicular to the surface. So finally, you will get phi equals to E times A, or the surface of the sphere. And the surface area of a sphere is 4 pi r squared. And then it equals to E 4 pi r squared. if you use Coulomb's law for E equals to Q over 4 pi epsilon r squared. And then if you take this E as this part from Coulomb's law times A is 4 pi r squared, you get 4 pi r squared to cancel. And then you get the flux equals to Q over epsilon. Epsilon is a constant which is related to the material. In vacuum or in air, epsilon equals to 1. So we define epsilon of vacuum or air to be 1. Then here, the flux equals to Q over epsilon for such a system, which is a spherical system. A particle charge. So this is the basic equation of Gauss law. Gauss law simply tells us the flux equals to Q over epsilon 0. Even though we derived this Gauss law equation by a point charge or particle charge, but actually this equation or the Gauss law can be extended to any cases. It's a very general rule or principle. The flux of a closed surface equals to the net charge inside this, this closed surface over a constant, which is epsilon 0. That's Gauss law. It tells us the electric flux through a spherical surface centered on a single positive point charge. The flux equals to Q over epsilon. This depends on amount of charge, but not on the radius of the sphere. So no matter which radius do you use, you can always get this equation. For point charge, electric flux is independent of R. So no matter which R you select, how big the sphere or spherical closed surface you choose, you always get this equation to be true. And then the electric flux through any arbitrary closed surface surrounding a point charge Q can be broken up into spherical and radial pieces. And the total flux through the spherical pieces must be the same as through a single sphere. For example, this is again the point charge. This time, if you don't draw a spherical surface, instead you draw arbitrary surface, still the conclusion is true. The flux equals to Q over epsilon. Because first the flux, let's say, no matter which surface you make, this is spherical surface, this is arbitrary closed surface, they have the same flux, right? As we said, any electric field line which go through the small surface should always go through the bigger surface because they're all enclosed surface and the net charge is inside. So any field line want to go out, it must go through all of the surfaces which are closed surfaces and contain this charge. So no matter which surface you choose, the flux is always the same. So here again, if you choose a surface like that, if you choose a closed surface outside a point charge, then what's the net flux for this closed surface? So it will be 0 because the flux, we can define flux to be the number of field lines going out of the surface. In this case, if you have one field line goes in, it must be going out at the other side of the surface. So any field line goes through the surface, goes in the surface, it must go out of the surface at the other side. So if you consider the whole closed surface, the going in and going out field lines equals to each other. So we can say the net electric flux for a closed surface when the charge is outside or out of this closed surface is always 0. It has no net flux. And now if you have multiple charges inside this surface, then the contribution of the total flux for any charge Qi inside the surface will be the net charge of those charges inside. For those charges outside, it doesn't make any contribution to the net flux because any field line generated, for example, by Q3, which is outside the surface, when it goes into the surface, it must go out from the other side of the surface. So for the charges outside the closed surfaces, they don't make any contribution. Only the inside or inner charges, they make contribution to the net flux. And the net flux, net electric flux is, let's say, it's depending on the net charge you have. For example, if you have one positive charge and one negative charge, they have same magnitude, then they will cancel each other. So the net flux will be 0. Only the net charge inside this closed surface is the source of flux. So here in the Gauss law or equation, here is a Q. Please remember this is net charge. You may have multiple charges, but the net charge is a source of electric flux. So let's introduce Gauss law officially. For any closed surface enclosing total charge Q in, the net electric flux through the surface is calculated by the surface integral, and then it equals to the net charge inside the surface over epsilon. This result for electric flux is known as Gauss law. Gauss law is a very general law. So in any case, if you have charges, you have a surface, Gauss law is always true. It's more general than Coulomb's law. Okay, so let's stop here. So from next class, we're going to apply Gauss law to some real examples, which will be very useful for your calculations for electric field.